I almost feel odd saying how easy it was for us, because it truly was easy. It was like changing configuration files. And I mean, there's definitely logistical challenges, and we're a very large organization. There are many thousands of services. So there's complexities around that. But the technical complexities were comparatively small. I think is a testament to both how well Google and ARM has designed this chip, as well as how much work the community probably has done.
Welcome to Nerd Out at Spotify, where we bring you behind the curtain of the world's most popular audio streaming subscription service. Machine learning, open source, clouds, tabs versus spaces. We'll talk to Spotify engineers about interesting tech issues, big and small. I'm Dave Zolotuski, principal engineer at Spotify. In our last episode, we talked about Google's Axion chips and how the shift towards ARM-based compute infrastructure is reshaping cloud computing. So what happens when you try to run thousands of services on brand new silicon? Today, we're getting into the how. I'm joined by Max Charas, a senior staff engineer at Spotify, who I worked closely with early in our Google Axion journey, and who's been leading most of the migration work. We'll discuss what it takes to bring Axion into Spotify's production environment, from early validation, benchmarking, and testing, to migrating real production workloads and getting everything to behave nicely on Kubernetes. We dig into the technical, logistical, and occasionally philosophical parts of the transition, from scaling and right-sizing workloads to the less glamorous side of working with brand new hardware at global scale. All right, let's get into it. I'm super happy to have Max on today. Max is, I don't know if I'm allowed to have favorites, but one of my favorite coworkers, and I work with him all the time. And this is a project that I work really closely with him on, so I'm super excited to talk to him about it. Max, can you just introduce yourself and tell me a little bit about what you do at Spotify?
Sure. Thanks. What a nice intro, Dave. My name is Max, and I work here at Spotify as an engineer. I work in a division called Core Infrastructure. We take care a lot about the basic infrastructure, networking, compute, the server side things basically that power the backend at Spotify. I'm actually recording right now from the headquarters here in Stockholm.
So tell me a little bit more about how long you've been at Spotify and your path to getting to the role you're in.
I've been at the company now for 5 years, always in the infrastructure area. And before that, I was working at Google, and I was working a lot with our Spotify migrations from our on-premise data centers to GCP. So I've been in orbit of Spotify for a long time now. And then before that, helping different kinds of customers build different kinds of systems, infrastructure, databases, distributed systems, all that good stuff.
And so then before the Axion migration stuff we are going to talk about, what are some of the other kind of fun things you did at Spotify after joining?
Oh, yeah. I mean, there were so many fun projects. One of the biggest projects was that we moved from Cassandra, the open source database, to Google's Bigtable, which was an amazing project, very rewarding, I'd say, in general. So that was fun. Right now, working on something in parallel with ARM stuff. I'm working on background coding agents, using AI to do coding tasks in the background that you can delegate to. So those are two really fun projects, one ongoing now and one historical.
Cool. I'm going to not ask you any questions about those because I don't want to turn this into an hour about that instead of what we're supposed to talk about.
I mean, yeah, I could speak so long about that. It's fun stuff.
All right, so let's jump into the compute stuff. So we want to talk about Axion, but first let's kind of set the stage. Tell me a little bit about compute at Spotify overall.
I mean, obviously we're a global service. We are running most of our stuff running on GCP nowadays. We used to be on-prem. We are deployed in 5 regions. So those are globally distributed regions, and we deploy in those regions for latency and redundancy. We're a classical microservice shop, I would say. So you can imagine thousands of services that support very critical things and some very niche and bespoke things. Most of the services are in Java and they run on Kubernetes. We also have a ton of data processing, obviously, that support much of our analytics and things like that. And then the services themselves, they're packed in containers, and teams then choose if they want to deploy in 1, 2, 3, 5 regions, depending on their needs. We also consider our regions to be failure domains. So you can imagine many of the regions to be similar in nature. They have much of the same services, and we can fail between them. And then when it comes to scale, we have many big services with thousands of cores, and then we have thousands of services that vary in size from, just a few compute cores to almost nothing.
And that's all on Kubernetes?
This is more or less all on Kubernetes. I mean, there is some stuff some systems that we do not run on Kubernetes, but most of it right now is on Kubernetes.
On managed Kubernetes, like Google Kubernetes, or?
Yes, it's all running more or less on GKE, which is a product that we use and love.
And I guess based on the numbers you said, I'm imagining that we have either huge numbers of clusters or numbers of huge clusters, which I think is a debate that people across the Kubernetes world have all the time. Where do we stand on that one?
Yeah, it's a good question. So we have a limited number of clusters per region. So we have a few very big clusters in each of our 5 regions. And for most of the engineers, when you deploy a service at Spotify, you actually don't know exactly which clusters you land in. You can figure out if you need to debug, but much of this is abstracted away from our engineers that want to just deploy a backend service.
Oh, that's super cool. So people don't necessarily interact with the clusters themselves. They just need to get their services up and running, and whatever they do for debugging, unless it's related to the cluster, you find ways of keeping them from having to know much about it.
Yeah, exactly. You can choose which regions you want to deploy in because you might have very specific needs, right? You want to say, actually, this services needs a very low latency, so then we need our 5 regions. But to your point, you don't need to know exactly which cluster you land in. You can figure that out if you need to debug something.
So then let's go one layer below that. Kubernetes, we all kind of have a feel for that, but what was the strategy for the infrastructure that Kubernetes is running on?
Maybe we should talk a little bit about the general type of workload we run, and then we can talk about the hardware there. Like the general workload is low latency services. They need to respond in milliseconds, not seconds. So we're low latency, but we're not super low latency. We're not like online gaming, but you don't want your playlist to load too slow. You want it to feel snappy. And Google offers a machine type called E2, which is a machine type that we used for a long time. They describe it as cost optimized, which it is. So you kind of sacrifice some of your performance for a better price point. These machines, they're quite small, at least if you look at it from the VM perspective, they're 32 cores and up to 128 gigabytes of RAM. So they're not big machines, but they are commodity. So they're very easy to get, they're comparatively cheap, and the availability is great. And then, of course, we have, some more niche needs. You might need more than 32 cores because you might have some vertically scaled workload, or you might need specific accelerators or specific, local SSDs. And in which case, in this specific case, we have other machine types that we offer as well internally to teams. But generally, our strategy was use E2. That was a good fit for most folks.
And that's across the board, backend things, data things. I was going to say ML things, but maybe not since you mentioned accelerators, but kind of if you need a computer, start with E2, and then we'll talk if you need something different.
Yeah, that was generally the strategy. I mean, Data used some other machine types for a while, or we used other machine types in Data for a while. But generally, if we squint, I think that was our strategy. E2 was a good fit unless you had specific needs.
And it sounds like that was largely for cost reasons, just because price performance wise they were great, or was there kind of more to E2 that I missed in your answer?
I mean, I think the ubiquity and just availability, there's such a commodity. It was always available, but I mean, primarily driven by the price point, I would say.
Price performance and always available wherever we need them. Google has plenty of them.
Exactly.
So that sounds like a pretty good place to be. So then why change? Why Axion?
Yeah, it's a good question. They are amazing, the chips that we're going to talk about. And I know you had Mo here at the last episode as well, but the Axion chips are really good. And when we did some benchmarks on them, we found them to be fantastic chips, simply. They performed much, much better, and the price point was good. It was just an all-around upgrade for us.
Were there other things that you were excited about in getting into using Axion and getting onto ARM?
I mean, I've been nerding out with ARM for a while now. I just find them fascinating chipsets. I mean, I started finding them interesting when I bought my first single board computer at home, these tiny machines, and just playing around with them. And I was just baffled by how fast they were. They basically drew no power at all, but I could throw quite complicated workloads on them. And as those evolved, it was just interesting to see what kind of workloads you could throw at them. And then I think my excitement really grew when laptops started using ARM. In 2021, ARM became much more prominent on the laptops, and it was just amazing to see the performance you could get and the battery time. And I think at that point, it just struck me that maybe this is something we should try on server-side compute as well. Fast forward a few years, and we spoke to Google, and they disclosed that they were looking into ARM and Axion. And given all of those nerdy reasons that I mentioned before, there was just, why not try it, right?
Yeah, I think I remember much of that. I didn't quite have as much experience playing with ARM, especially not at home with kind of single board computers and things, but I remember looking a lot in cloud. I remember the first laptops I got with an ARM chip and all those same things. Like it's just faster, it's got better battery life. It seems very obvious that anywhere where we care about power and compute is going in this direction. Of course, cloud is a place we care about power and compute. And I remember those couple of meetings with Google when they were first telling us about it, where afterwards you and I would get together and be like, so we've never tried these things. We have no idea. Google doesn't have them yet, but we're doing this, right?
Yeah, exactly. It's just super interesting to see that the ARM offer come out, and super exciting.
And at first it was exactly that. I remember like a call we had with some people from Google that were telling us under NDA about these. Mm-hmm. And then that was a week or two before Cloud Next. And at Cloud Next, I met those same people and they didn't really have any more to present to me because they literally had just talked to them. And so those 20 minutes, I just basically spent telling them that as soon as this exists, I want it, and I think I want all of them. And they were just like, well, let's see how it goes, and let's like get some and test it. I was like, nope, I want all of them. Let's just go.
Yeah. And I mean, that's kind of where we are right now. We're just grabbing as many as we can.
Yep. Anyway, let's tell the story in order. You and I got very excited about which a corporate strategy does not make. How did we get from you and I are excitedly sending each other Slack messages about these things to your org actually doing a lot of work in the compute space around these? Like somehow you got access to these things and tested them and validated that it was the right thing for Spotify and not just something that would nerd snipe both of us?
Yeah, we had to do some due diligence, obviously. So we got some early access machines from Google, and then we ran a bunch of synthetic tests on them, like CoreMark, NetPerf, Unix Bench, things like that. And they just showed the same numbers as Google presented to us. So that validated at least that we were seeing a very good performance uplift. And CoreMark, for example, showed more than a 2x performance uplift compared to E2, which was great. I mean, that's a huge uplift. And also here, I think it's interesting to state that it's both the per core speed that goes up, but also I mentioned before that E2 is only available in up to 32 cores and Axion is available up to 72 cores. So if you actually look at the whole machine, that's over 2x per core and over 2x in number of cores. It's a huge difference in a per server capacity.
So on that note, why do we care about per server capacity?
As I said, we run Kubernetes clusters, so we have all of these small Dockerized pods running on the machines themselves, and we want to bin pack these as much as possible. But we don't want to bin pack them too hard, because if a single workload bursts, we don't want to run into 100% CPU utilization. So we always want a little bit of overhead on top to make sure that no single workload is starved of capacity. And when you have 32 cores, say that you want a 10% margin on top, I'm just inventing a number here, then that's a 3.2 cores margin on top. But if you then move to a machine with 72 cores, if you want to keep the same 3.2 cores, percentage-wise, that's a much smaller number. So essentially what I'm trying to explain here is that you can bin pack more, and we hope that we can get more performance out of a single machine.
Yep, I got you. So it's not just that we care about per core performance and if we can always get more boxes, but the actual box per box part matters too. Was there value in the fact that also means we can have fewer actual VMs? Does a large number of VMs cause problems? There
are definitely problems with that, like number of IP addresses. And there's also just toil if you want to iterate over all machines. There's a lot of overhead of having so many thousands of servers. So just from a toil perspective, having fewer servers is better. So that's definitely a thing. The other thing I should mention here also is that having single cores that are faster, you can have fewer replicas of your service, assuming that you are CPU bound. And that hopefully then also translates in having less amount of RAM in total. So if you have 10 replicas on E2 and then you have half the amount of replicas on the Axion machines, so you're down to 5, then that also halves the amount of RAM that you're requesting, assuming that you have a constant amount of RAM per replica. So there are a lot of benefits of having faster processors and bigger machines, I think.
And then you mentioned E2 as more of kind of commodity hardware, not just less cores, but were there other advantages we saw? Because Axion is new, it comes on new hardware, so I don't know, the motherboard, NIC, insert random component that is also in that rack with it is now brand new instead of having been there since whenever that E2 was put in the data center.
Yeah, I mean, most of our workloads are CPU bound. So the thing that we look at most is CPU, but we haven't observed any other bottlenecks on the machine. And if you look at the specs that are presented by Google, you can see a great performance uplift in essentially all dimensions. It's a new server, so like a faster network card and, faster memory speed, new disk types, basically all of it. But as we are CPU bound on most of our workloads, at least these kind of serving workloads, that's the primary dimension we look at. Interestingly, we have a few workloads that we also saw great benefits on latency. And we don't really know exactly why. We haven't had time to dig into that, which is, honest truth. But there have been some astounding results in latency improvements as well.
Yep. So there's also just a little bit of magic in these things. So we should keep it up.
Yeah.
I think you talked a bunch about the testing we did with benchmarks and things. How do we validate that actually carries over to real Spotify workloads?
Oh, it's a good question. Yeah. So the next thing we did after these synthetic workloads is that we took a few real services and move these over to Axion. And then we simply measured the performance increase and saw, and we wanted to see, on par with what we saw in the synthetic benchmarks. And we actually saw better results than the synthetic benchmarks, which was fantastic to see. Why? Again, a little bit of magic. We don't know exactly why, but it was good. But generally, we saw a performance uplift in all dimensions that we needed to see a performance uplift with. So in practice, that was just switching over to deploying one of these Dockerized Java services on the ARM machines.
Yep. And that was just to take something that was kind of representative of most workloads.
Yeah, exactly. So we chose a couple of services that we thought represented the average kind of workload at the company. And then we ran it for a few days, just verify that in fact, our own workloads followed the same kind of pattern as these synthetic tests.
Yep. That makes perfect sense. Were there kind of non-typical things, like maybe extreme cases where you really wanted to test something because you thought it might benefit way more, or maybe be a good reason not to move to Axion or something? Or did you just test a few representative things and then decide that represented enough so we can move on?
We tried a few other things as well, more bespoke things like transcoding. But generally, I would say in that specific phase, we were more time bound. So we were prioritizing a result rather than spending too much time on it. As you enter an actual migration, you can continuously evaluate as you go as well. In that specific case, we chose a few specific services. Now, obviously, we have migrated much more, so we can continuously track and see if those metrics are on par with our early tests.
We didn't explicitly talk about the team, but I'm guessing this was like a pretty small, let's do some testing to make sure it's a good idea to invest more in. And it sounds like at this point, everything's gone well. You're still excited and want to move on. Let's talk about the next steps. How does this become an actual thing that your org is doing as opposed to let's validate some new technology?
So now we kind of did the technical due diligence. There is also a phase of financial contractual due diligence with the cloud providers and, seeing that, in fact, from a financial perspective, it makes sense because if you see a 2x performance uplift, you also want to see some kind of comparable financial gain as well.
You want to see a less than 2x cost increase?
Yes, hopefully, right? So that's definitely a phase you go through the contractual things. And then I would say the next phase after that was the infrastructural work. So there's a ton of infrastructure work that you need to do. And it was pretty unglamorous work. So, I mean, you and I, Dave, we converted a lot of like base images and Docker containers and just making them ARM compatible as an example. And that's really not difficult work to do. It just needs to be done. It's a few lines in a Docker file. The larger piece of work is actually provisioning node pools for these GKE clusters and seeing that we have actual physical machines to deploy on. So that we had the commercial phase and kind of the infrastructure phase. And then after that, we started moving some kinds of services over.
I love the kind of very quick way you can gloss over making these things build for ARM, just because everything we run is Java and Docker containers. And almost always you just add build for ARM and that works. But there are so many random idiosyncrasies in our build process that sometimes would fail. And then for many other companies that aren't Spotify, that don't just run Java on Docker, that one sentence throwaway of, just make it build for ARM is like its own engineering disaster.
Yeah, no, 100%. I mean, I almost feel odd saying how easy it was for us because it truly was easy. It was like changing configuration files. And I mean, there's definitely logistical challenges and we're a very large organization. There are many thousands of services. So there's complexities around that. But the technical complexities were comparatively small. I think is a testament to both how well Google and ARM has designed this chip as well as how much work the community probably has done for years and years with ARM compatibility that we're just benefiting from.
Yep, exactly. I think it's also a bit of it, like I wouldn't say we're behind because I think it's like huge percentages and probably most of cloud customers are not running on ARM.
Yeah.
But because we're doing this now and not before there were Apple Silicon MacBooks, like I think I remember when we got our first M1 MacBooks, there was a ton of this like, this isn't going to build or this isn't going to run. We need to get some other library. And I think this time around, there were just a handful of examples where like, we haven't updated this dependency in so many years that we can't use the ARM build of it. And when we update it, I don't know, 5 API calls don't exist anymore. So we have to fix that. But it was all in that order, not like rebuild your whole thing for ARM.
100%. And I can just imagine these waves of compatibility investment with, the Raspberry Pi wave. You probably have a huge investment in Android, making that work, iOS, obviously, and then the MacBooks as well. So yeah, we totally benefit from that. And it's been easier than I want to admit.
Yes, but that was great for us, at least.
Yeah.
So then it sounds like we've done a bunch of validation. We've started getting some of the infrastructure together. Then what? How did we actually do the migration? How much have we migrated? How do we even decide what goes first or last?
Yeah. So looking now at the type of workloads we've moved, I see like 3 broad categories. So there's the standard workloads that we call the golden path or golden state workloads. They follow a fairly standard template, and they can be either data processing or backend services. We mentioned the backend services case, it's Java services on Docker. For those types of services, migration is pretty easy in that we can do that centrally. We can change the base templates for Docker images and the templates for CI/CD and the deployment systems. And most engineers at the company, they don't have to do anything. And then you have another category of workload, which is large platform-y type services. Those, as an example, would be our perimeter, could be our caching infrastructure, search infrastructure, and things like that. They're not standard in any way. They're very bespoke and specialized workloads. We have moved both of those 2 classes, so kind of the standard backend workloads, we have moved a good chunk of them. And then these large platform services, we're kind of going step by step and moving them as well. What we haven't touched is what I would call the long tail of workloads, the things that aren't golden or very large in any of those 2 categories. And that could be, your weird Python thing running over here that somebody just created a few years ago, or like a WordPress instance or something like that. And I think it's still kind of up for debate how much we want to move of that.
Yeah, and I guess why would you say that stuff hasn't been touched yet? Just because you're not sure you want to move it? Or is there kind of more to it than that?
I guess if you need to do hands-on engineering work on it, even small amounts of work like changing the Docker image, because maybe it uses a custom Docker image, this workload, engineering work is expensive. And if it's a tiny workload, it just uses, 1/10 of a core or something, then there's a question of, is it worth it? And I guess that's a debate we need to have, because I firmly believe that we will always have non-ARM workloads, because there will always be specific needs. The question is just, is it worth moving these kind of the long tail?
And I guess you mentioned some things being bespoke, even in these large ones. Do you have any interesting surprises there, or all of this was kind of, it just builds for ARM like we just joked about, you're kind of good to go, and then it's just a matter of flipping it over to a different node pool?
I mean, our perimeter, I think, was a fair investment to get to work. That work took some time. Then for our caching infrastructure, we use memcached. And I think in that case, it was also just, I did part of that work, just literally changing the base image and using an ARM-compatible release of memcached. There are certain cases where it's a little bit harder. There might be an open source framework that doesn't have ARM compatibility, as an example, or an ARM release, and in which case there's potentially more work to be done. And I would say those are like 2 categories of work. Either it builds on ARM, it builds fine, but there's no release for ARM, or nobody's even tried running this thing on ARM. And those are 2 vastly different categories.
Yep. Adding all of these things up gets to a probably fairly phenomenal amount of scale at this. So I imagine there's a lot of, outside of the details of each workload, overall process around this move. Can you talk a little bit about making it all line up and figuring out when what moves and how it works? And I imagine working with Google to make sure it all works.
Yeah, I mean, we joked about everything being super easy, and this is where it doesn't become super easy. The move to ARM for us has been a logistical challenge more so than a technical challenge. We have a couple of limiting dimensions for us. One is which workloads we have validated work on ARM. Another is actual available capacity that Google can provide us. And the third one is discounting models that we have contractual things with our cloud provider with Google, right? So you can have a committed use discount over multiple years, and those are bound to a number of cores. And when those expire, you would want to sign a new committed use discount or kind of move your workload. Now, if we look at these three dimensions then, so capacity is regional. So you get a number of cores in a specific region. These committed use discounts are also regional. So you have these expiring discounts in a specific region at a specific time. And then you have to match that with the available services or workloads that you can migrate. And those can also have different topology in different region. So what it boils down to is basically a great temporal 3D puzzle, which is hard. Yeah.
That's not just somebody on a spreadsheet somewhere?
I mean, that's what the whole world is, somebody on a spreadsheet somewhere, but it's a big spreadsheet. And yes, there are trade-offs and math, and it's been an interesting challenge.
Yeah, no, I think, yes, I've been involved in a bunch of those bits and pieces too. Yeah. And it's had its moments.
Yeah.
One kind of fun thing that we read into, I think, was some of the zonal stuff we did with Memcache that I think was a kind of an unexpected surprise along the way. Can you talk a little bit about that? Just because at least I thought it was interesting.
Are you referring to the zonal skew?
Yes.
Yeah. So we deploy equally between our different zones. We try to keep equal capacity in our different zones. So if we have a service with 10 cores in a region, we want to keep 3.3 cores in the 3 different zones. These services have different type of dependencies, and obviously one of these dependencies can be a cache in Memcache. Now, our Memcache installation at the time was designed so it would prefer the local zone the service would deploy it in. So if you would have a service with a Memcache, then the replica in a specific zone would try to talk to the Memcache replica in the same zone. And obviously this can be sharded and scaled and so forth, but that's the gist of it. Now, what happened was if we would get zonal skew, so we would have 90% of capacity in zone A and only 5% of capacity in zone B and C, we would get this very big skew that resulted in some incidents where we would hotspot or overload Memcache in a specific zone. And it actually took down, I think, our entire US deployment of Spotify for a few minutes before we were able to fix this. But those are things that you learn during the way.
Yes. Slightly more fun.
Mm-hmm.
Talk to me a little bit about sizing on these things. I mean, these instances are clearly kind of faster and better, like we said, in almost every dimension.
Yeah.
And our services are used to running on much older commodity things. Mm-hmm. So I imagine it's not just like divide it by 2 and YOLO.
Yeah, I mean, kind of almost, but then it turns out that's not enough. So when we scale our services, we have an autoscaler. Most of our services use horizontal pod autoscaler in Kubernetes, and workloads then set a CPU target. So they might set a CPU utilization target of 60% or 50%. And then if their average CPU utilization goes over 50 or 60%, then the horizontal pod autoscaler adds more replicas to this thing. Now, and this is great. And in theory, to your point about YOLO, if you move to a 2 times faster processor, the number of replicas should just shrink in half. That, in theory, should be great. But the problem is you can set things like minimum replicas. So, and if you set your minimum replica count too high, then it turns out that you are basically wasting a bunch of capacity because your horizontal pod autoscaler can't scale low enough. So when you actually look at our entire ecosystem, it turns out it's not as easy as YOLO. And likely what we need to invest in, and we haven't done yet, is more automatic right sizing that kind of introspects the CPU utilization and capacity of a specific service and changes the parameters to make sure you're not wasting capacity. And we call that right sizing.
And you mentioned before that, like when you were talking about performance metrics and things, that during the migration, we can do a lot of continuous tracking of this sort of stuff. Have you done continuous tracking, and have you seen that we're doing better or worse or staying at about where we expected?
We are doing pretty good, I would say, in general. If you look at the services that follow the pattern where YOLO applies, they follow that pattern of shrinking by something like 2x, which is great. But there are a lot of corner cases where YOLO doesn't apply. And that's really where we need to spend more time. So I would say we're not tracking as good as we wanted to initially, but there are plenty of things that we can do there, with right sizing as an example being one of them. It's also interesting to mention here that we have chosen to expose any engineer building a backend service at Spotify to the raw deployment and horizontal pod autoscaler settings of Kubernetes, which requires you to set request of RAM and CPU and CPU target. And one of the things that we're exploring as well on this is maybe going more towards like t-shirt type size abstractions, where you say, I want a small machine and, I want 50% CPU utilization. So that's something that we need to figure out how to do that abstraction. But generally, to your question, we are doing not as well as we wanted to, but that is primarily for the reason of right sizing.
Yep, that makes sense. So then along the way, kind of anything I missed, any fun surprises or things that have gone, I don't know, particularly well or particularly poorly that we should have talked about?
We touched on a few of these, but what I want to say here is the honest answer is like there weren't any surprises. It just worked amazingly. And, that's kind of not completely true, but from a technical perspective, it was actually much easier than I initially thought it would be. Compatibility-wise, things worked great. Most of our things were already working on ARM because of the MacBooks being ARM now. As I said before, I also think it's a testament to how much the community has done and Google has done. The things that surprised me maybe is this temporal 3D puzzle and the logistics and complexity of that. The fact that this hardware is not completely ubiquitous and there are different capacity schedules in different regions and contractual things. That kind of logistical thing was perhaps a surprise to me. And I've seen some fairly big migrations before. This one was more complicated from that perspective than I anticipated.
I think at least to me, it seemed like most of our big migrations were software migrations. And this is a hardware migration. And I think that was a thing that we struggled with because we weren't used to all of the logistics and details that come with that.
Mm-hmm. Yeah.
But maybe I'm misreading it.
No, I think you're right. I mean, even to a certain extent, the migration from on-prem to GCP was also kind of a software migration. And we have kept on these E2 machines because they've served us really well for a long time. So we haven't really been needing to do this type of hardware migrations where we've been limited by other non-ubiquitous dimensions. Real world servers. We don't think about that too much.
Yes, exactly. When we were thinking deploy something in a data center, we meant send some bits down some wires. And when we talk, exactly, now we talk about deploy in data center, and it's like, well, the truck shows up, the thing comes off the truck, and it needs to get plugged in.
Exactly.
It's been a while since Spotify was having those conversations.
It's been a fun journey. But yeah, for anybody that wants to undertake a migration like this, that's maybe one of the things to not underestimate.
Do you have any advice for others that are kind of looking into doing this sort of migration, or maybe even this specific migration?
If you're interested, do the benchmarks. And if it turns out to be good, just go for it. That's maybe the first thing. And the two actual, maybe more tangible advice is, if you're operating at scale that we do and you have thousands of services, just plan for the need of right sizing in some capacity. Just think about the fact that the underlying hardware is going to change in so many dimensions that either you have to accept that everybody will have to go through the journey of changing their hardware parameters of their workloads, or you have to have a plan to do that automatically. And then the other part, I would say, we haven't really spoken about that, is think about how you're going to do CI and CD. If you run exclusively x86 and you introduce ARM, what are you going to do about integration tests? Are you going to just assume that things work because you're running Java? Are you going to run maybe a nightly compatibility build on ARM to see that it works? Or do you want to go the whole way and run both builds in parallel on both architectures? And I guess that depends on the type of workload that you have and maybe the type of CI systems that you have invested in.
When I was asked the same question, my version of go for it was like, don't trust people's benchmarks, even though what we've seen them be right. Like, just run some stuff. Yeah. Because for us, it was so easy to just run some stuff that we did it. But also in just running some stuff, we learned that our CI and CD would work here. And I think if you go to just run some stuff and it's incredibly difficult, then the benchmarks don't matter. You have a different engineering problem right now.
Yeah, 100%. It also, I think, doing the initial benchmarks also shows you potentially how complicated your path to ARM is going to be. And if it turns out that your benchmarks are dead easy to run and you get good results, then you know likely your path to migrate is fairly easy or maybe easier, and you have some tangible results.
So what's next? What are you doing now in this space? Or going to be doing soon, maybe? If you're still
I've hinted to this. Like we need to do some right sizing, obviously, some automatic right sizing. And I think one of the interesting challenges there is just to think about what abstraction level we want to be at when it comes to our workloads. Because now we're kind of at the lowest level where people say, I want 5 cores and 8 gigabytes of RAM. You can imagine a slightly higher abstraction level where maybe people say, I want a medium-sized machine. Or you can imagine a more of a pass/functions world where people just consume and there are hard limitations, upper limitations, but essentially you shouldn't have to think about hardware at all. So that's one of the challenges that we have right now. And then I think that the goal of this is obviously to make it easier for people at Spotify, engineers at Spotify, to just deploy a service and not have to care about this at all. So that's one of the challenges I really look forward to digging into next.
Yep, that sounds super promising. So I'm excited to see that.
Me too.
Hey, Max, thanks a lot. This was a lot of fun.
Yeah, thanks for having me. It was great.
Aside from Axion and maybe ARM, what else are you nerding out about?
I mean, now my life is like autonomous coding agents, but I'm an avid gamer also. I'm playing through the whole Diablo game series. So I just passed through Diablo 1. I'm at the end of Diablo 2. So I'm really looking forward to going through all of them.
If I remember correctly, that's old enough that it wouldn't run on any hardware you probably have today. So how are you even doing that?
Blizzard has kindly done remastered versions of most of these, which is amazing. I had a lot of compatibility problems on Diablo 1, actually.
Yes.
But I got it to work. And I could play the whole thing. I don't even know what most of these buttons do, but there's like compatibility mode in Windows and stuff, and I had to click around a bunch of these different things and read it, but I got it to work.
Diablo 1 just brings back memories of high school, building a... what were they, like 3DFX, whatever the like pre-NVIDIA and ATI taking over the GPU world graphics cards were, like Windows box for one of my friends who wanted to play Diablo.
Exactly. Let's just say I didn't have any performance problems with Diablo 1.
Yeah, Direct 3D was awesome.
It was running smooth on my gaming PC nowadays. It was a good blast from the past playing that game.
Thanks for listening. To learn more about Axion, check out the link in the show notes. Nerd Out at Spotify is produced by Spotify's Sarah Tazari and by Seaplane Armada, who wrote our highly optimized theme song. I'm Dave Zolotuski. Thanks for nerding out with us.